Hi everyone, I'm Bruno from MOVEdot. Welcome to episode 6 in our tutorial series where we're developing a sports car as we study VI-CarRealTime together. Today, we'll focus on vehicle stability and we'll work on the kinematics of our car using SuspensionGen, a tool included within VI-CarRealTime. We'll use it to investigate the potential to make the car even better and faster while ensuring that the car is still safe and stable under transient maneuvers, such as double lane changes. Let's start. From the File menu, start by loading the Track Car tutorial session, so that we can go back to working on it. Let's create a backup for the current state of the car by right-clicking it in build mode and cloning it. Select the clone and call it trackcar_EP05 as it corresponds to the development we did in the previous episode, and select the track car database. Select the clone's main folder in the tree view, save all, and delete it from there. In Vehicle Dynamics, Kinematics define the wheel movements and orientation, both of which are properties of the suspension mechanism's design. On top of that, we have compliance, mostly defined by the pivot's bushings. Kinematics can be designed for different goals, like helping a street car provide efficient tire wear for long periods of travel at modest speeds, and also helping track cars perform their best by providing optimal tire positioning in high-performance applications. Even though our initial kinematics are based on those of a sports car, they can be further optimized, and the changes we made to ride height when implementing the aero package can have influenced them negatively. We will be paying special attention to the following metrics as we investigate and develop our kinematics. Bump steer, since our suspension is now operating in a different range than it would in its original design condition, so we should look at how the toe varies with relation to jounce in this new position to make sure it doesn't present undesired behavior. Camber gain around the new range should also be studied, as it will help control tire wear and will influence the car's limits under braking, corner exits, as well as mid-corner balance. And stability can also be greatly influenced by the roll centers, which themselves influence load transfer and jacking forces. In most cars, the chassis hardpoints are deeply connected to the structural design, and we will avoid changing them. What we will do is focus on adjusting the outer hardpoints, the ones on the upright, because doing so allows us to act on all of the factors we need while only requiring the redesign of the suspension arms and the uprights themselves. Luckily for us, we don't have to worry about compliance, because the original sports car suspension already came with rigid joints that we can keep in our updated design. Suspension subsystems in VI-CarRealTime can be defined either as template-based models, which are multi-body type, as they are described by the hardpoints and their flexibility properties, or as curve-based models, which basically describe the wheel's positions and angles with relation to jounce, loads, and steering. Each has pros and cons, and ultimately, VI-CarRealTime will only use curve-based models to run dynamic simulations. So it will create a temporary curve-based version of whatever template-based system is present in the car model before it can perform a test. Our car's suspensions are curve-based, so their files don't hold information about the hardpoints directly, and generating a multi-body representation of the original mechanisms from them is not trivial. Gladly, VI-Grade provided us with the original design files for the sports car suspension that we will need for this tutorial, and you can download them from the video's description. Extract the file and drag its contents to the folder where the sports car suspension files are stored by following the address on the screen, starting from your VI-CarRealTime's root folder. To analyze and develop kinematics, we will use VI-SuspensionGen, available from the Utilities menu. As we click to launch it, we can make a choice between opening the preset model for one of the many types of suspension that can be represented here. Instead, click Load Suspension from File, navigate to the Sport Car database, select the front suspension double wishbone 09 file, and open it. When launching SuspensionGen from VI-CarRealTime, as we just did, you can access the databases that are registered to your work session. The file we opened is the original design for the front suspension of the example sports car that we just downloaded. SuspensionGen's user interface is split into three main sections. To the left, we find the data table, where we can edit the parameters for the model that is currently loaded. It includes tabs referring to features that are relevant to this specific suspension layout, like the anti-roll bar in this case. On the bottom, we can run the Kinematic analysis. Go ahead and click it. Doing this enabled the two buttons on the right. That allows us to export text and MATLAB files containing the analysis results, and export this model as a curve-based suspension subsystem that can be directly loaded into VI-CarRealTime. Running the analysis also populates the plots on the bottom right, where we can observe the curves that fully define this suspension's behavior. We can right-click the tabs to create more plots, like it's done in VI Animator. The 3D display on the top right shows what the suspension looks like right now, and will update in real time with every change we make in the data table. Note that the plots will not update in real time. They will only update after running a new analysis. Make sure to do this before exporting a modified suspension model. We can rotate, zoom, and pan around the 3D display, and on the View menu, we can also find more options to manipulate the camera. The sliders let us see the suspension in all the analyzed positions, and even roughly animate it. To easily find the data for a hardpoint, we can click it on the display and it will be highlighted on the table. Each hardpoint can be edited for its position through the coordinates we see here, according to this coordinate system. The suspensions will be applied to the car according to the wheel center in the x-axis, so we can only focus on each point's relative position to it. We can also edit the hardpoint's linear elastic properties, its rotational elastic properties, and its orientation. On the top, we can make the suspension symmetric, so that both sides are mirrored, or asymmetric, so that we can design each side to different specifications. Some hardpoints may not include elastic properties, like these ones on the bottom, and the hardpoints available will change according to the suspension layout that's currently loaded. To enable elastic properties for a hardpoint, select the bushings tab, navigate to the one you're looking for, and check the upper box. We can also edit the properties of this bushing in detail in this screen, allowing us to define nonlinear behaviors. Installation components, such as helper springs that act in series with the main ones, can be activated and defined here. In the General Data tab, we will find the properties for the main springs, dampers, and stoppers. Some settings that are exclusive to this suspension's layout, like this one that allows for selecting what to attach the anti-roll bar link to, and some information about the vehicle this suspension is designed to be applied to. These are important for the calculation of anti-dive and anti-lift effects, as well as jacking forces, and they will also update the dimensions of the wheels in the viewer. The Setup Data tab allows for the definition of the suspension's base toe and camber. Enabling setup values allows us to do an extra tuning step before running the kinematic analysis and exporting the results. As usual, on the main menu, a help file is available for information on more advanced resources. And here, we can create a new SuspensionGen suspension file, load an existing one, or save our current project. If we drag the jounce and steer sliders to 0, we can see the suspension at its design condition. But this doesn't mean it is working around this position when our track car is moving. Currently, after all of the development we've done in the previous episodes, the front suspension sits roughly 69 millimeters lower from the design condition when the car is at rest. And we can slide to the right to see what the kinematics looks like when closer to that height. Toe variation around this height shows towing in upon further compression and out in extension. Meanwhile, camber variation around this height is at its most sensitive region. The instant roll center is very low, standing below ground level at this point. Don't worry about following along this next step, but if we would look at the rear suspension, this is what we would see. At rest, the rear suspension is lowered by around 75.5 millimeters from the design condition, where it looks like this. Here we can see a tendency towards towing out in compression. The camber gain, once again, is at its steeper region, and the instant rear roll center is also very low, but higher than the front one. Despite kinematics like this being acceptable, we can tune them to provide more predictable handling to the car, while ensuring stability and maybe even allowing for a little performance gain. We will approach this problem like this. By slightly raising the static roll centers, we expect to allow for the car to transition faster, while remaining less reliant on spring stiffness to control body roll. By redesigning the rear suspension so that it tows in under compression, we can guarantee more stability in heavy side-to-side load transfers and at low-speed acceleration situations. And by reducing camber gain around the current rest height, we can make handling more linear and thus more predictable, and the car more prone to respond better to static setup changes. Modifying the kinematics may affect much more than the points we are interested in, so we have to also pay attention to things like the motion ratios, Ackermann, caster, kingpin inclination, and scrub radius, as we reposition hardpoints towards our desired behavior. This is an iterative process where we can develop many solutions to analyze, compare, and refine suspensions. For the sake of this video's objectivity though, we're only going to recreate the final solution we came up with in our process. Also, know that if using template-based suspension subsystems in VI-CarRealTime, it is possible to run investigations regarding the positioning of individual hardpoints by using coordinates as factors to optimize the suspension at a component level. Let's begin updating our front suspension while paying attention to key characteristics around the rest position, with the weight of the car suspended by the springs, instead of focusing on the design condition, where it was before we lowered, so that we can maintain compatibility with all other parameters we updated so far in VI-CarRealTime. We already have the original file loaded in SuspensionGen, so on the data table, let's update the hardpoints locations according to the table on screen. Move the upper control arm outer pivot point to Y equals minus 764 and Z equals 380 millimeters. Move the lower control arm outer joint to Y equals minus 774 and Z equals 170 millimeters. Also change the tie rod's outer point to Y minus 760 and Z 171.8. And move the springs and dampers lower mounts to Z equals 180. Let's head to the General Data tab and on the top, connect the anti-roll bar link to the lower control arm. Then scroll down and select non-linear springs and browse for the track car's front spring property file within its folder in the working directory. Set preload to 5,500 newtons and scale factor to 1.65. Doing this here means the suspension will be exported according to our current specifications, and we will not need to readjust everything after loading it into VI-CarRealTime. Select the non-linear front dampers and browse for their property files too, according to the investigation we ran last episode. Enable and browse for the bump stop with a clearance of 10 millimeters and the rebound stop with a clearance of 40 millimeters. Now navigate to the anti-roll bar data tab and set stiffness to 15.5 newtons per millimeter. Once this is done, we can run the kinematic analysis to update the model files. We can browse the results tabs to see how the changes we made affected bump steer, camber variation, and roll center progression. When we're happy with the updated suspension, we can click Export CRT Subsystem, confirm the first prompt, and navigate to the track car's suspension folder, where we can save the file as track car front suspension. Also select one of the alternatives for naming the steering subsystem that will be created alongside the front suspension itself. Let's also save our project file so that we can further edit it in the future if we want. Click here, navigate to the same database where our original design files are located, and save it as front suspension track car 01. We can now close SuspensionGen and, on build mode, replace the subsystems corresponding to the front suspension and steering with the ones we just created. We still need to make some adjustments here, but we will get back to them later. For now, open SuspensionGen again. Choose to load a suspension file and browse for the rear suspension double wishbone 09 downloaded earlier. Go on the data table to change the following hardpoints. Move the upper control arm outer pivot point to Y equals to minus 715 and Z equals 105. Set the lower control arm outer joint to Y minus 720 and Z minus 103. Change the tie rod's outer point to X80, Y minus 729 and Z minus 78. And set the push rod's outer point to Z equals minus 88. In the General Data tab, on the top, leave the push rod connected to the upright. Scroll down and select Nonlinear Springs and browse for the track car's rear spring property file within its folder. Set preload to 6,500 newtons and the scale factor to 1.3. Select the nonlinear rear dampers and browse for the rear property file. Enable the bump stops and browse for their respective files too, with a clearance of 10 millimeters. And do the same for the rebound stop with a clearance of 270 millimeters. Let's go to the anti-roll bar data tab and set the stiffness to 41 newtons per millimeter. In the analysis data tab, set the jounce range between minus 40 and 100 millimeters with 10 steps, and run the kinematic analysis to update the model files. We can observe the new tendency towards towing in on jounce that we designed for stability. We can now export the CRT subsystem to the track car's suspension folder as track car rear suspension. Let's save this suspensions project file too. Click here, navigate to the sport car database and save it as rear suspension track car 01. Then close SuspensionGen and head back to CarRealTime. Change the track car's rear suspension subsystem to the one we just created and click Apply to reload the updated model. If we browse through the front suspensions tabs, we can observe the info we set on SuspensionGen is already here, like the property files for the springs and dampers. We will, though, change some more settings starting in the anti-roll tab to match what we had previously. Change its type to rate and set the value to 15.5. We also need to re-implement our car's static setup at the appropriate tab. Set ride height adjustment to active. Change both Z values to 150 millimeters. The ride height values to 69 millimeters, and change the method to push rod. Now go to the wheel angles tab and activate everything. Set toe to minus 0.75 degrees and camber to minus 4 degrees. So we have the same setup as before. In the Components tab, deactivate all 4 bumpers. Let's do our final adjustments to fully implement the new rear suspension too. Navigate to the anti-roll tab, change its type to rate, and set the value to 41. Go to the suspension setup data tab, activate it. Set Z to 150 millimeters and ride height to 75.5. Under wheel angles, activate all of them. Set the toe values to 1 and camber to minus 3.5. In the Components tab, deactivate the pin height variation boxes and the 4 bumper clearance boxes. Let's click the steering subsystem now. Change steering inertia to 35,000 and damping to 45, adding some detail to the steering feedback for when the model is used by a human driver. With this, we can click Save All to register all updates to the database, completing all changes we will make to the car today. Let's head over to Test Mode and set up a simulation to observe how the track car responded to the new Kinematics. Browse the bookshelf for the Press Maneuvers event, right-click it, and add it to a new fingerprint with the track car. Then, find it in the tree view and select it. The Press Maneuvers event includes many tests where the car won't follow a predetermined path, having to freely navigate around a set of obstacles instead. We will use the double lane change consumer report because it demands very quick reactions and rewards response and stability, so select it on the list. These settings allow us to define the initial state for the first iteration the driver will attempt. If it successfully completes the maneuver without touching any obstacles, it will attempt the test again at a higher initial speed, and will keep repeating this process until it can't avoid hitting objects anymore. Set initial velocity to 30 km per hour, initial gear to 2, and set refinements as 2. Select this box to use body chassis graphics to define the volume that will be considered when the driver attempts to drive around the obstacles. Save the event, find the event in the tree view again, and duplicate it. Select the copy and set it to use the EP05 backup model we made earlier. Also rename it accordingly and save this event too. Save the session, and with this, we can select the fingerprint containing our double lane change maneuvers and click play to run the simulations. When the simulations are ready, let's head over to Review Mode, select their fingerprint, and open their results in the animator. By hitting play, we can observe the best result for each car. It's a transient-heavy test, where the car quickly swerves back and forth between two lanes, like if dodging a wide object on the road with barely enough time to take a cornering set. The updated car was a bit faster here, completing the maneuver a little earlier and with a more constant speed, suggesting an improvement in agility. If we observe the steering profile, the first plot under the Driver Demands tab, we will notice the new car requires more steering around the apexes of this maneuver. We can also observe a smoother, more dampened steering profile as the car straightens out of the last transition, with no overshoot. Both of these are indications that our changes to the roll centers and toe variation led to a more stable car. If we would plot the body roll data, we can see a decrease around the maximum values, as desired, meaning we do, in fact, need less loads at the springs and anti-roll bars to control that parameter. If we would compare lap times at Calabogie right now, to have an idea of how much these changes affected our performance on a racetrack. From a standing start, the new car is also faster. We can close the animator and head back to VI-CarRealTime, where we can save our fingerprints and save the work session to conclude today's activities. In this episode, we improved our track car's stability by fine-tuning its kinematics. We did this by further discussing about suspension modeling in VI-CarRealTime, learning how to use VI-SuspensionGen to create and edit kinematics and their properties, using high-performance events that do not rely on predetermined paths. Kinematics are powerful, being able to severely influence how a car behaves, but they're also delicate, as a small change aimed at improving one thing may lead to unwanted side effects in others. As an example, moving an outer hardpoint a little farther out may influence the motion ratio, inducing a change in overall balance too. The tools we use today are ideal for this type of development since they provide us with a comprehensive view of how the car responds to such changes. When combined to the many resources we've been using throughout this series, it lets us analyze and develop virtually all aspects of vehicle dynamics in a safe and efficient environment. Stay tuned for the next episode where we will create an electric variant of the track car and rebalance it with an extensive fine-tuning session. I'll talk to you soon.